Welcome to the multivariable calculus section. Today we'll be discussing the equations of lines and planes. Here we have the three-dimensional equation of a line. It is r is equal to r naught plus tv. Now t is a scalar here, and we are coupled with three other vectors, r naught, and v. So a scalar, all it is just a multiplicand, like it's a multiplicand, anything that can multiply the value of our vectors. So let's say we have a scalar like 2, 3, 4, any arbitrary number. Anyways, so let's try to figure out why our three-dimensional equation of a line is the way that it is. So here we have a three-dimensional graph. We have our x, our y, and our z, and we have the vector tv, and we have r naught, and we also have this red dot, which is p naught, an arbitrary point indicated and comprised of x naught, y naught, and z naught. So here we are given our equation of a line because the TV gives a direction to our r naught, which means that we have a line, because if we look at the definition of a line is comprised of a direction and a point, any arbitrary point, which means that this would give us this. Okay, so we don't want to write it down like this every single time. It is very useful, but we can also parameterize this equation, and we can get x is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct. And these are our equations of a line. But if you notice, each of these equations are relatable through this value t. Now, we can say that t is equal to x minus x naught over a. It's also equal to y minus y naught over b, and it is also equal to z minus z naught over c. And this is deemed our symmetric equation of a line. This is pretty useful because when you want to substitute or you want to find any one of these values, all you need is 3 of the 4 and you are good to go. So now that we know the equation of a line, we are going to look at the equation of a plane. So we know that equation of a plane can be given through an arbitrary line and an arbitrary point. Before we had a direction and a point for a line, so we need a line and a point for a plane. So our point can be given through the r minus r naught, because when you subtract two vectors, you're left with a point. And here we're dealing with r and r naught. Now our line can be given through the normal vector to the two vectors we're dealing with. Because we're dealing with two vectors, and before we learned the cross product, we know that a cross b will give us the normal vector between these two vectors. So if we do r cross r naught, we are also given the normal vector between those two vectors, which is a perfect utilization. So now we know that the n dot r minus r naught will give us our equation of a plane. But hold on. We don't want to write it like this because this is very difficult to format. We can also write this equation as such: a x minus x naught plus b y minus y naught plus c z minus z naught is equal to 0. And that is the equation of a plane that we will be using a lot. Okay, so let's try a problem now that we know all this information. Now here we are given 3 points. We have P is at 2, 3, and 5, Q is at 4, 7, 9, and R is at 8, 3, 1. Sorry. So we have a 4-step process if a problem asks us, write an equation of a plane given the 3 points. So first we want to establish our 2 vectors, and we'll label those vectors A and B in this point. Establish A and B. And so that'll give us our lines. Now we want to find our normal vector. So in order to find our normal vector, we will do A cross B. So that is our second point of interest. Now our third point of interest is to find the equation or the normal vector and line up the components. So the normal vector will produce AI plus BJ plus CK, and we want to correspond these A, B's, and C's to the A, B, and C of our equation of a plane. So the x naught, the y naught, and the z naught actually comes from the original point of the line. So say we were to do two vectors such as PQ and PR. The original point is going to lie with the P because we are drawing something that looks like this. And we know that our P naught is going to start from this point, which is actually P. So P naught is X naught, Y naught, and Z naught. Okay. So now that we have that, we'll say, find the equation of the plane given the 3 points. So first we want to establish our A and B. So PQ is A and PR is B. And we're just doing this to line up to our formula. So we have 4 minus 2. Oops. Let's rewrite that. We have 4 minus 2, 7 minus 3, and 9 minus 5. We're finding the difference between the 2 points to get our vector. And then we also have 8 minus 2. We have 3 minus 3, and 1 minus 5. So we know that A, our vector A, is equal to 2, 4, 4, and our vector B is equal to 6, 0, negative 4. Okay, so now let's find the cross product between these two. A cross B is equal to I, J, K, 2, 4, 4, and 6, 0, negative 4. Okay, perfect. So let's do this. Let's do the expansion form. Oops, that is in miscellaneous line. Let's do the expansion form. IJK 2, 4, 4, 6, 0, negative 4. IJK 2, 4, 4, 6, 0, negative 4. Perfect. So let's do I. Let's do our J and our K. Okay, perfect. So we have negative 16 minus 0 is our I. Okay, let's write this actually over here. So we'll do negative 16 minus 0 is our I, minus negative 8 minus 24 is our J, and our K is given by 0 minus 24. That is our K. So we have negative 16I plus 32J minus 24K. And so this is our A, this is our B, and this is our C. So now we know that our X naught, our Y naught, and our Z naught come from this point P, 2, 3, 5. So we can actually write our equation out given this information. We know that our A is equal to negative 16. We know that our X naught is equal to 2. We know that our B is equal to 32, and we know that our Y naught is equal to 3, and we know that our C is equal to negative 24, so we'll write negative 24, and our Z naught is equal to 5, which means that this is our equation of a plane. Now, if you need more help or more problems to do for equation of a plane, we have some on the website, and I recommend those. Thank you so much.